Okay, so in today's talk, what I want to discuss is how you move actually from the use of imaging biomarkers from a single site to multiple sites to make it actually usable in a real world. So first, let's talk a little bit about imaging biomarkers. And to start with, I'd like to say that they have multiple uses. There's a number of things you can do with imaging biomarkers. I'll show you some illustrations with some specific diseases. First, for differential diagnosis, this is an application where you have two diseases that look very similar, but they're not the same. So one of the things you can do for multiple sclerosis, for example, is to look for little veins inside lesions, as you can see here on the bottom. And this will tell you whether this person has multiple sclerosis or something that looks like multiple sclerosis. You can use it as well for determining whether somebody is eligible for an intervention. We had a talk about stroke before, so this is one of the things that you can look at for stroke with perfusion imaging. You can look at regions of the brain that have a restricted perfusion. This is the case here on this map, which is already produced using a convolutional neural network. And using this, you can decide whether you want to do this mechanical intervention or not. Two other things you can do for drugs: you can test eligibility for patients, and you can also test for adverse effects. So in the case of the recently approved Aduhelm drug for Alzheimer's disease, for example, it is in fact part of the label that you have to look for some abnormalities in terms of MRI. And also you can check for adverse effects. So here you see one of the adverse effects that you have with Aduhelm is the presence of cerebral microbleeds. And these are, look, you see these tiny dots here on the image, that these are microbleeds. You can also follow this up with imaging biomarkers. Of course, you can also look at the drug response. So in the case of multiple sclerosis, again, if you have longitudinal imaging, like here on the left, you have a lesion at some time, and then after some drug effects, you have this lesion that has become smaller. So in this case, the patient is responding to treatment. So that sounds very much, all these examples I gave you sound very much like computer vision tests, right? So you can think, well, let's train a neural network. So here in this talk, I want to say not so fast, because things can change very quickly. So one of the things we're working on now in the lab is actually looking at how these imaging parameters can impact image similarity. So here you have an example of one brain, one person. And what we're going to do now is vary just 3 of the imaging parameters you can change, which is the flip angle, the bandwidth, and TRTI. You don't need to know what they are, just know that they are modes of variation around this image. So this is the same subject now with other flip angles. The same subject again with a variety, as you can see, of TRTI parameters, and the same again with different bandwidth. So you see that you have noise that is non-homogeneous spatially, and if you have temporal data, you also have this in the time domain. And this is in fact, this little simulation here, the same patient is scanned about 14 times, is in fact very optimistic, because all of the other parameters are the same. We're not changing the resolution. It's the same scanner, it's the same antenna, it's the same scanner OS, it's the same operator, no repositioning, and same date. So this is in fact, you see already with varying just 3 parameters, you see how much diversity you have in these images. The reality is more like you have a number of these things to account for. And this is just one modality, one organ. What does this mean for machine learning? Whether you're doing handcrafted features or doing automatic detection and end-to-end learning, you will have an effect of these acquisition changes. Here's an example. This is a biomarker called connectivity, functional connectivity, whereby you measure blood oxygenation levels in the brain, and you look at this in multiple parts of the brain. Then you look at whether different parts of the brain consume oxygen roughly in synchrony. And from this, you can measure temporal correlation, and you can get a graph, which you see at the second step here on the left. If you have a graph, then you can do graph embedding. You can extract features from this. One of the simple things you can do, you can just count the number of connections, so the number of regions that are strongly connected or correlated with a particular region. Okay, and this is what you see on the left. From this, then you can try to distinguish between your populations. As an example, I'm showing you here data from autism. So in red, you have the patients, and in blue, you have the controls. These are a number of patients using 90 brain regions. And so what you see is that you have higher strength. So this is the strength of connectivity for some regions, typically for the control. So this means that you would say that autism is characterized by hypoconnectivity. You have lower values of this biomarker. Great. So now let's look at the same values at another site. And you see now that the picture is much more complicated because now this distribution has shifted. And now you have actually some regions of some patients that are actually more connected than regions of control. So this shows you that you can have an effect. And it's not only the case for handcrafted features, it's also the case for automated detection. So here I want to show you an example for multiple sclerosis again. On the left, you have the same patient in one scanner. On the right, another scanner. This is a very nice study where they actually looked at 17 different scanners. And you see this little arrow on the bottom left showing a lesion on the left side that you cannot see on if you're using another machine. So this is fairly strict. This affects both humans and machines. So the biomarker you can derive from this is you detect all the lesions, then you count, you aggregate them, the volume of them, and this is called the total lesion volume. It's a marker of disease status and disease progression. So let's look at how this varies across sites. So on the vertical axis, you see this total lesion volume. Horizontal axis is the site. The black dots are manual segmentation, manual detection, and the bottom is this estimation using automated tools. So you see first that you have a lot of variation between humans and machines, but of course that's expected. But you see also that you have a huge amount of variation between the sites. In fact, so much so that about 90% of the variance is explained by site. So now by now, I hope that I've convinced you that the problem is not as easy as it seemed before. And so what can we do? Well, you can either take this problem head on. If you have no data and you're starting to acquire data, you can do prospective standardization. But if you already have data, then you have to do retrospective approaches using machine learning. For prospective approaches, you have a number of things that you can do. First, you can try to standardize the acquisition. This is very common in the industry, but it is very disease specific. Here I'm showing you two examples. The first for ADNI, the Alzheimer's Disease Neuroimaging Initiative for Alzheimer's disease, which has a set of protocols for a number of machines. And the second is MSPath for multiple sclerosis, where it is also the same, that they're trying to harmonize these acquisition protocols as much as possible. So this is something that is great, but it's a lot of effort because everybody needs to agree, and it's very disease specific. The second thing you can do is something called quantitative imaging, where, for example, modalities like magnetic resonance imaging are not natively quantitative. They give you some values, you have some contrast, but it's not like 10 in one scanner does not mean the same as 10 is another one. One way to deal with this is to do quantitative MRI, and that means, for example, that you will measure the relaxation times of proteins. So you get now milliseconds, which in theory should be very, very similar across sites. So this is one way to deal with a site problem that is extremely promising. Here's an example from the Siemens scope in Lausanne, where on the top you see a control, on the bottom a matched patient, and you see that some inflammation is clearly visible on the bottom that you don't see at the top. And so the nice thing with this is now you can say, well, this relaxation time is like 300 milliseconds, and you can compare it with another site. This is not entirely solved at all for cross-vendor issues, though. And the last thing you can do is feature standardization. So then you can agree on how you will compute features once you have some data. And this is very much a hot topic now in the field of radiomics. And you have multiple initiatives worldwide, some in Europe, some in the US, that try to address this. But it's not always the case that the data is to be acquired. Many times you're given data that is acquired and it comes from multiple sites and you have to deal with it. So what can you do? There's three main things you could do. First, you can change the data. So this is that you have data from one side, the grid site, and you transform it into data that looks like it came from the other side. So these are things like image-to-image translation, for example, that you can do. Second thing you do is to change the training. So now, for example, if you have data from multiple sites, you could do, for example, transfer learning from one site. You pre-train your model with data from one site, then you adapt using data from another site. And lastly, what you could do is also change the model. So one thing you could do is try to learn latent representations that are invariant to site. And so there's also a lot of work around this. So I now want to illustrate the first and last approaches, changing the data and changing the model, and skip changing the training for now. If you want to change the data, one of the models that works the best these days is called the generative adversarial network. And this is a network that used to be very difficult to train a few years ago. Just even 4 years ago, it was kind of hard to get it to converge. Now it's getting more and more commodity in a sense. It's still a complicated model, but I would say now it should be part of the arsenal. So what it does is it tries to generate this type of model that try to generate data that looks as if it came from another site. And then you have another part of this network that tries to distinguish between data from the site. And you basically try to fool what's called the discriminator. This works. You have one approach called conditional GAN, where you need paired images, and you have another approach called the cycle GAN, where you don't necessarily need to have the same patient in both sites. So this is actually more promising for real-life applications. Let me show you an example of where people have used that. For example, this is from the group at UPenn and others, that basically they have a site A, let's say that they want to translate to, that they want to universally translate to some kind of universal approximation. So what they have is they have a set of reference data that they will try to translate all the data to. So they transform the data, and you see that the site B data here with a quote unquote, this is actually data that was generated to look like it came from site B, even though it came from site A. And the result of this is actually quite promising. For example, in a simple age prediction task, they reduce their prediction error from like 15 years to 7 years. So about half the error is pretty good, just by doing this harmonization retrospectively. So this type of approach, I think, is very promising also for segmentation and for abnormality detection, these kind of things. The main advantage of this is that you do not need to touch the other algorithms. If you have a favorite segmentation algorithm, then you can actually use it without the change. This is often the case, in fact, that you do have tools that are there, and you want to have data, you want to adapt the data to them without changing the tool. Also, if you have situations where you have the tools that are FDA approved, for example, it's not that you can retrain them necessarily very easily and retain the FDA approval. The other thing you could do, as I mentioned before, is to change the model. So typically, all these approaches, they always have some component that penalizes the site differences. So in your loss function, what you will add is not only like a data fidelity term, but you will also have something that gives you a bad score if the images that came from different sites look too different. So one approach which is nice is this one that I cite at the bottom. This is for segmentation. And essentially, what they do here is they add a number of terms that actually try to affect this site difference penalization. And so what they do now is they segment a number of brains from two different clinical protocols, one called ADNI1, the other one called ADNI2. And they do 90 regions. They compute the volume of these 90 regions. This is called volumetry, and this is quite useful for clinical purposes. And from there, they can actually learn from this 90-dimensional representation. They can learn a 2-dimensional representation using any embedding technique. In this case, they use t-SNE, but they can also use UMAP. So on the left, you see here the pre-harmonization, on the right, the post-harmonization. And the argument here is that if the embedding, if the projection in the embedding space is closer together post-harmonization, then you're doing a good job actually of matching the two sides together. So this type of approach is also, I think, very promising and has, I think, a lot of potential for solving real problems. So if we compare these approaches, prospective versus retrospective, first, the main strength of prospective approaches is that if you can do it, you're going to acquire data, you might as well go for it because you prevent future problems. For retrospective approaches, the main strength is that you can leverage the literal millions or tens of millions of images that you already have acquired in clinical centers. So just in Lausanne, we have several millions of images from patients that are basically mostly, for the most part, used once. And so using these kind of approaches of harmonization retrospectively, we can probably leverage them and do very good machine learning. The effort, if you're doing prospective approach, is really on policy. You need to convince people to adopt a certain protocol. You need to convince radiologists that maybe they have a different perspective. So this is more like, it's not really like a technical thing. Retrospective approaches, of course, the approach is more on the technique. You have to put a lot of effort on the technique. In terms of disease, as I was saying before, prospective approaches are pretty specific in terms of acquisition because not all diseases will be imaged with the same sequences or with the same device indeed. For feature extraction, things like radiomics, this is a bit more generic and not sensitive to disease. In terms of ML, it doesn't matter that much what the disease is, although machine learning has problems with small features. Typically, if you have like very small lesions or aneurysms, this kind of things, this is actually very tricky to deal with, even with modern methods. And finally, the vendor focus. Prospective approaches, you can standardize for basic protocols very easily. It's much more difficult to do for advanced protocols, and retrospective approaches can do this kind of inter-vendor standardization, but you need a lot of data. So in conclusion, I think you should do both if possible. And of course, pre-processing is often neglected, but very basic, simple things, like adaptive histogram equalization, these kind of classic things from image processing, they still work very well and they're necessary. So to conclude, I hope in this 15 minutes I've shown you that domain shift has very severe negative effects and should be combated. That it is a hard problem in terms of machine learning because you have high dimensionality. Noise is non-uniform, spatially and temporally. Effects are non-linear, so this is a hard problem. On the plus side, they can be mitigated prospectively if you have the luxury of defining your protocols, and they can be mitigated retrospectively if you can change the images, the models, or the training strategy. So all in all, I think that this issue of domain shift and how to combat it in medical imaging, I think basically it holds the promise of very, very impactful research, both basic and applied. And I'm not alone, of course, in thinking that this is just like a quick listing of the workshops and the challenges just this year that are around this topic. So I would like to thank the lab members that did, in fact, most of the work, the collaborators, and of course, the funding, and you for your attention. Thank you very much.
Thank you very much, Jonas, for highlighting it, for sharing, first of all, with really interesting findings and thoughts, but also highlighting that essentially in the ML research, it's not, the question is not always about access to the data. I mean, this pre-processing and being able to sort of, take into account all what you highlighted is really, really important for, essentially for transferring what we learn in research to, medical practice eventually. So thank you very much.
Absolutely.
Now, one of the questions that we have is for the ML-based approaches, how much dependency would you have on some sort of a ground truth to exist across, let's say, Skinner or data acquisition platforms to be able to sort of, build out those systems?
So this is a very, very interesting question. So maybe let me answer it in two parts. First, I insisted a bit, I didn't really want to delve too much into technical details. There's, of course, a number of techniques that are unsupervised. So this is probably maybe even the hottest part of all this topic is how to do this without annotation. Maybe you just have annotation about the site. So there's a lot of work on these invariant subspaces that you actually just need information about which site it comes from and you don't need anything about the disease. But what you said about the ground truth is actually particularly important. This is something that I've even hidden here, even in my kind of a pessimistic / optimistic talk. There is, in fact, also the notion of label shift. So you do also have the fact that there's not only the domain shift from the center of the hardware, but also different medical practitioners have different opinions. And in some cases, like multiple sclerosis, this might be actually as big a deal as multi-centric imaging. So you don't necessarily have the same clinical practice, and inter-rater agreement can be low. If you have big lesions, it's very easy, everybody agrees. If you have small lesions in MS, not everybody agrees. So this is actually also, this ground truth is very important, but it's also important to recognize the uncertainty in terms of these labels.
Good. Thank you. Another question for you is more on the protocol-based approaches. And the question is, would protocol-based approaches sufficiently reduce variation, meaning that a mixture of both approaches is needed and possible? And especially if you were to contextualize it as you give the example of Alzheimer's drug, and then essentially a need for imaging as a something to monitor for adverse events, and then probably this protocol-based approach becomes even more important. So again, in your view, would the protocol-based approaches sufficiently help reduce the variation in this work?
So I think it would be, if you have the luxury of doing it, I would think definitely that would help a lot. So that really depends also on the vendors. This is something that I mentioned, but this is really crucial. Like, it's very difficult to do things that work across multiple vendors. But I would say, indeed, because you could also think maybe you don't need machine learning, right? So that's also something that maybe, of course we want to do machine learning, but maybe you don't always need machine learning. But already just with the same protocol, you can reduce a lot this inter-observer variability. So maybe that is sufficient if you don't need machine learning. Now, I want to say, If you are to do machine learning and you can get the protocol very, very close, that's going to be much easier. And maybe you don't even need these harmonization approaches, but I think it depends on your task. That's the answer. If you're doing things like atrophy detection, like in Alzheimer's disease, if we talk about this disease, if you want to detect atrophy within 6 months, it is very, very tough, even with the same machine. So in this case, if you're further switching the protocol or switching the machine, that gets even tougher. So I think that for, let's say, large features, large things to detect, large abnormalities, protocol harmonization, I think gets you 90% of the way there. But for small things, small shifts, you need a bit more creativity also on the machine learning side.